Hi everybody, Thomas here from my channel Astrophysics. Well, let's start with this short animation you see here from Wikipedia about an asteroid called 2024 PT5. The name is here at the very top. And the asteroid itself is this purple dot flying around. The blue dot is surprisingly our home planet Earth, and this dot here is the moon. We have here other parameters as well, like the daytime on the top left corner. We have here the velocity with respect to the Earth and also the distance to our blue planet. And of course, you may know that, well, orbits like the Jupiter around the Sun, the moons around Saturn, our moon around the Earth, or the Earth around the Sun, they are pretty predictable orbits, like circles, elliptical orbits that behave normally. What we see here is very strange, and we will not compute the orbit today of this object. In another video we will do it. It won't be a compressed cosmos series, it will be a smaller project, let's say. But the reason of the shape here is apparently the gravitational influence of our home planet. Of course, we have the moon, we have the Earth, we have the sun, and so on. And this requires heavy numerical computations, like for example, the ones you can do easily in Universe Sandbox. Thankfully, though, there are some concepts that allow us to reduce this complexity to a very small equation, to a very short formula, to something that considers the gravitational influence of the sun and the Earth in a way that we don't have to consider the sun anymore. And, well, what are these kind of concepts? Well, that's something for us to figure out today. Well, and always we have our code here in my GitHub repository, Thomas/Astronauts YouTube tutorials. Now, I already have 150 stars on this repo. I'm pretty glad that more and more people are taking a look in my repository. Now, if you find these things interesting, just give it a star so you won't miss any updates, because I mostly update the core code earlier than the videos, so you will be the very first one. Now, for today, in a Compressed Cosmos series, we have to click on Compressed Cosmos, and then we go here to Compressed Cosmos _ gravitational influence. Now let's click on this one. And the good thing is we don't need anything to install on our computer, because we have the small batch called Open in Colab. Now, if we do this, as always, everything is being transferred to a Google Cloud instance that is also available for free in the free tier subscription. First, let's connect to some instance, and in the meantime, we talk about two concepts today. The first one is the so-called Hill sphere. Now, the Hill sphere is like a theoretical sphere around the Earth, like it's a concept, an approximation that considers the semi-major axis of the Earth, the eccentricity of a planet, so it doesn't have to be the Earth, it has to be an object, primary mass, like for example here it would be the sun, and the secondary mass. Now, the secondary mass is the object of with these parameters, semi-major axis and eccentricity. Also here it is the Earth. It will return the Hill sphere radius in meters, and the Hill sphere is now the part where objects like, for example, an asteroid, or also our home, our moon, can find a stable orbit around the Earth without being perturbated too much by the sun, so it will fly away. And the equation is pretty simple, so a lot of text here to give you some understanding and feeling, but the equation is pretty simple. It's basically just the semi-major axis times 1 minus the eccentricity, considering the secondary mass divided by 3 times the primary mass plus the secondary mass to the power of 1/3. Now, I think if you see the video, you will see now the equation. And this is a pretty simple single liner you can use to compute this Hill sphere for any object. Now, here in this case, I have a test case. The Earth data, I obtained the data also from Wikipedia. So let's execute this run. Yes, I trust my own code. and we get the Hill sphere, which is 1.4 million kilometers. Now, if you consider the moon, it's only a fraction of this 1.4 million kilometers. So as long as the moon is not going away too much, our moon is stable around our home planet and is not being perturbated by the sun or other planets too much. So that's a good thing, I would say. The other thing is something called the sphere of influence. Now, the sphere of influence considers only the semi-major axis and both masses, and it is a slightly different formula. Let's go here. Where is it? It's also pretty simple. It's the semi-major axis times secondary mass divided by the primary mass to the power of 2/5. Well, let's put the equation again here. And what does it do? Well, this computation is basically used by astrodynamics people for spacecraft stuff. Yeah. So for example, we shoot a spacecraft into space and we want to get some energy, let's say with a flyby at Venus or Mars or Earth. Then we can also do some numerical simulations. But if we want to use a two-body problem, so only considering Earth and the space probe, we can use the sphere of influence where we can switch between the sun as a reference frame to the Earth. So we have the sun, we compute the orbit of the spacecraft around the sun. Now it touches the sphere of influence. We switch to the reference frame, which is then Earth-centric, continue computing the spacecraft orbit, and then when it touches again the sphere of influence, we switch back, and then it flies away, and we see how it gained maybe or lost some kinetic energy. We'll do some examples in the future. I think you have maybe heard about this concept like flybys and so on. And instead of heavy computations, you can use the sphere of influence. Now, let's see the sphere of influence here. Oh, I spoiled it already. Nice, but let's execute it anyway. For our home planet, it is smaller than the Hill sphere. It is 900, well, yeah, around 900,000 kilometers. Now, both spheres apply not only for the Earth, but also for Jupiter and Saturn and all other planets as well, and also their moons too. So this is like a very basic building block for any student who's, for example, working in astrodynamics, or for a student who is working with spacecraft trajectory data. You can really use these approximations to simply switch between sun-centered and Earth-centered coordinate system. And how are we going to do it? Well, in the future videos soon, we will talk about it. Until then, happy coding and see you next time.